Log on, tune in, find out. Another good idea from Cambridge.
Afternoon seminars. So we have the pleasure to introduce Jochen Heinloth, that is going to talk about the introduction to a motivic point of view on the cohomology of Moduli spaces of bundles and curves.
Thank you very much. So first of all, I'd like to thank the organizers for the invitation to be here. It's a great pleasure, and for the invitation to give this talk. And this is sort of a bit special because I not only was asked to give this talk, but I was asked to give a talk on a particular subject. So this was completely commissioned by Oscar. And so the main point of the talk is sort of to try to convince people, if this is necessary, that there's no need to be afraid of the Grothendieck ring of varieties, and that it's sometimes nice and useful to do your computations there, if you can. So if you're not afraid of this ring, you're safe to leave now. I mean, there's no so then there's no additional point I will make. And so in particular, I will not give any new results. Yeah, I mean, this is all well known and work of other people. Yeah, okay. So that's for the introduction. So, but how does it come about? I mean, so the point why we did, why Oscar asked me to do this is that we did some computation of cohomology of some moduli spaces, and well, it turned out that it is sort of very useful to do this in a more general setup. So the starting point was that. Well, Oscar likes to compute Hodge polynomials of moduli spaces, and I'm coming from a different. I mean, I did my thesis with Harvard, so I'm much more used to do point counting over finite fields, and so the Grothendieck ring of variety just turned out to be the common ground to do both things at the same time. So that's the only point. So let me start to just recall a bit about this ring and the motivation to introduce it at all. So this is just a recollection. So how could you possibly come about this? And this is probably how this was first used by Kontsevich. Okay, so recall that if we have an algebraic variety over C, then its cohomology has the extra structure of having a Hodge structure. So then the cohomology of your variety has an extra structure. So it's, well, let me be a slightly bit imprecise. So it has the nice feature that it has a decomposition. Well, it's isomorphic to the direct sum to these. Such a thing. It's has a Hodge structure, and it's probably mixed. So if you vary, so if X is smooth projective, then this is just the usual Hodge decomposition. Yeah, and this is the Hodge decomposition. Okay, so and for my talk, it will be sort of more useful to put compact supports on my cohomology everywhere. But this, I mean, if you think of smooth projective varieties, then it doesn't really matter. Yeah. So everything I tell you will more have a flavor of a homology theory than a cohomology theory. So it's easier to do cohomology with compact supports instead of cohomology. But this is a fine point which you can ignore for some point. So what do people do if they try to compute the cohomology of moduli spaces? Then in most of the setups, they calculate actually the Hodge polynomial. Namely, they encode the dimensions of these spaces in a polynomial, just as you would do. And so this is called, for compact support, it's called the E polynomial. So you get the E polynomial. This is just like the Poincaré series of your variety. So this is called E of x. I mean, it's it depends on x, but it also is a polynomial in two variables, u and v, and it's just defined to be the sum. Well, you take the dimension of these spaces, and then you let u count the number of p's you have, and v the number of q's, and then you put a minus 1 to the k in front. And why would you do this definition? Yeah, this has a, so this has this nice property that it's actually an Euler characteristic. So this has an extra property. If you have Z and Z a closed subvariety, then this is additive. Then E of x is E of x minus z plus E of z. And yeah, this is, I mean, there's really, this just comes from because you have a long exact sequence for cohomology with compact support. I mean, this you all know, probably. Yeah, and so I mean, this is an alternating sum, so you have an.
So in the definition of E, it's also cohomology with compact.
Oh yes, thank you. So I will sort of, yes. And so this is why I use compact supports, because in cohomology you would not always have this. I mean, even if all your varieties would be smooth, you would have a Gaussian sequence, but then this thing would be shifted in cohomological degree, and this is sort of annoying to carry around. So this is sort of easier. And there's really nothing more to it than to have this. So, and why is this sort of useful? Yeah, you may imagine if you construct a moduli space of vector bundles or something, then you might be able to stratify it into pieces that you understand well, and then you can calculate the cohomology of the pieces, but then you would usually worry about computing these differentials. Yes? So, but the funny thing about this is, as I told you, if I have a smooth projective variety, then these, well, I said this is the Hodge decomposition, so only terms appear where k is the sum of p and q. So if I have a smooth projective variety, then this polynomial will determine the dimension of the cohomology groups. Yeah. So in particular, as long as I know that the final variety I want to compute is smooth and projective, I can forget about all differentials while doing the computation. Yeah, I'll just compute this polynomial, and in the end I'll say, well, I know by a priori that my variety is smooth and projective, and so I can read off the Hodge numbers. Yeah, so this is just so the point is just to say that this is a trick to say we don't worry about differentials at all, as long as we know a priori that our variety has pure cohomology. Yeah, so that only terms. So maybe let's fix this. And Ex determines the dimension of the HPQ if we know that the cohomology is pure. So if we know that HKPQ is non-equal 0 only if k is p plus q. This is called q. So if for some reason we a priori know this, then we can just do our computations without worrying about any differentials. Okay, so that's the whole trick that we want to use. And then of course you think that, okay, if we want to consider some moduli problem and we want to compute our cohomology of the moduli space by stratifying it, and the only rule that we know uses this additivity of these E polynomials, then we should do the whole computation in a geometric way and just compute with the classes of the varieties. So that's sort of the universal Euler characteristic, and that takes values then in the Gaussian degree. So that's just formalizing, constructing your variety by cutting and pasting of subvarieties. Yeah, so the universal way such invariant, this takes values in the Groton degree of varieties. So what is this? So this is just the free abelian group generated by isomorphism classes of quasi-projective varieties. So this is a huge ring, and then you impose one relation, namely you impose this cut and paste relation. You say that the class of X should be the class plus the class of, yeah. Okay, so this was maybe, yeah, I don't know. I mean, this carries the name, this is the Groton degree of varieties. So and apparently this carries its name justly because it seems that Grothendieck really wrote this down first, but it was never used until Kontsiewicz used it for his famous result. So that's this. And so now this is a huge ring, and so we will, yeah, and I mean, of course, if you write this down with this relation, you know nothing about this ring. It could be zero, but it is not because we know that the for example, this E polynomial gives us a homomorphism from this ring to polynomials. Yeah? So we have properties. So the first is that this ring is really non-trivial, so that the E polynomial really defines a homomorphism from this to polynomials in U and V. Yeah? Just because you just define the E polynomial for X, well, it satisfies this relation, so it gives you the thing. So the second thing that you notice, that this is really a ring. I gave it to you as a group, but it's of course a ring. You just say that the product of two classes is the product. And you immediately check that this is compatible with the relations. What else? Yes, so the important thing that we will use all the time is if you have a fibration, is a fibration with fiber, say F, then of course you know, well, locally trivial just means that you can cover this by open such that the inverse image of an open is U times F. So you can you cut and paste your variety into two pieces where it's actually such a product, and so you see that this will be the class of X times F. Yeah?
Locally trivialing the Zariski topology.
Yes. Yes. But this is very restrictive, but I mean, that's as good as it gets in this ring. But I mean, it's restrictive, but it's still useful. Yeah. So yeah, let me give some examples. I mean, first do some very easy examples. So of course, okay, I should define this. So the class of the affine line is usually called the Lefschetz motive, or it's called by L. Yeah, it's just this is just the affine line. So so what classes could you compute of this? Yeah, so yes. So then for example, you could compute the class of GLN. Yeah, using this. And what will you get? I mean, maybe I should ask the public. Yeah, then maybe just write it down and then I ask you whether it's obvious. Yeah, so yeah, so you will find that the class of this is just invertible matrices. Yeah, and you find this result just by linear like in your linear algebra course. Yeah, I mean, what is an invertible matrix? Well, you choose the first column. You can choose any vector, but you are not allowed to choose 0. So this gives you L to the n minus 1 minus a point. Yeah. So the second column is allowed to be any vector, but it's not allowed to be in the span of the first vector, and so on. Yeah. So at every step, adding another column will tell you you can choose any vector, but not in a subspace of dimension the vectors you have already chosen. And this is actually a locally trivial fibration argument that I give you. And so this is really the formula. Yeah. So the yes. So the next thing I want to have is, of course, I would like to in the end tell you about how to compute the class of the moduli space of vector bundles on the curve in this ring. Yeah. Just as an example, and this was first calculated by Behrendt and Dillon, well, building on previous work, of course, by Bifegion and Letizia. And to tell you this, I mean, I first have to tell you what do you actually mean by computing this class, yeah? Because I mean, I can just take the moduli space to brackets around it, and then I have the class, and this doesn't tell you anything. Yeah, so computing the class means expressing it in terms of varieties that we know well. Yeah, and so so as you might expect, the type of varieties you will encounter, I mean, if you would try to compute PIC, which we will do in a second, then the symmetric product of your curves will be important. Yeah, so this is another thing that you can do. Another example of a computation is first for any variety, let me denote by, will be impossible for me to stick to one notation, but so this is just the symmetric product that you take the ith product of your variety and divide out by the symmetric group action. And then people define the zeta function of x. So this is defined for anything. And this is just the formal power series. This is called the zeta function of x. And this has the nice property that this is now something multiplicative. So note and there's really nothing going on here. I mean, this is just because, yeah, if you take the ith symmetric product of I, then this is yeah, I mean, you can just stratify this into how many points lie in Z and how many points lie outside Z, and then you get this formula. Yeah. Okay. So in particular, this again defines me something for every element in K0 of varieties. Yeah? Because so let's compute a few examples. So the first maybe is yeah. So what's the zeta function of L? I mean, you just have to take the symmetric product of affine spaces, but these are just affine spaces themselves. So this is the sum over L to the I times T, and this is just 1 over mod minus L times T. That is just a geometric series. There's nothing happening. So then this, I mean, if you know this, then you know this because of this relation. Yeah? So it's just 1 minus LT. So this, let me do it slowly. So it's the class of the affine times the class of a point. And this is and now comes a, so now I take B, a smooth projective curve. which will be the case for most of the time. And I mean, I don't know if there are any algebraic, any more arithmetic people in the audience. And for what follows, I will assume that my curve has a point, and if you think of the complex numbers, then you forget this. Then I claim, and this is then you have a result of Kapranov. And Kapranov computed the zeta function of this curve, and he found the following very nice expression for it, which is sort of very familiar if you, know these point counting results. And what you find is the following, where so it's p of t times the zeta function of the projective line. So this p of t should be the zeta function of c minus the projective line, and that's what he puts here. So this is, if you think in terms of cohomology, the c minus p1 will just have the h1 of the curve. Yeah, this to write c minus p1 in the Groton degree is just a fancy way to write the first cohomology group of your curve. Yeah, because the cohomology of p1 in degree 0 and degree 2 is the same as the one for the curve. Yeah, so this is a formal combination. And then the funny thing, and then you should, if you just do the same with usual cohomology, then you think that here should be the Poincaré series of the exterior algebra of the h1 of the curve. And this is what you write down here. So the sim becomes an exterior product. And because this is confusing, I want to prove it. I mean, I give you an argument why this is true.
Use a t to the I, no?
Yes, of course. Thank you very much. Yeah, and the funny thing is that here you only have a finite sum to 2 to the g. Yeah. So we know. So you know already that the zeta function of the curve is the zeta function of p1 times the zeta function of c minus p1. So the only thing you have to check is that you need to check that if you take the zeta function of the curve and you multiply it by the numerator, by the denominator, sorry, then you will get a power series, and you need to check that this, if you take the coefficient, so you need to so this has coefficients of t to the I equal to 0 for e bigger than 2g. Yeah, that's the only thing you have to check. Yeah, you just take this on the other side, and then you get this term, and the only thing you have to check is that you actually get a polynomial in degree 2g and not an infinite series. So you just write this out, what this means. So this is the same as, let's compute the ith coefficient. So what is it? Well, here there's just the sum of the symmetric products. So I just write it down, and you tell me if you complain if you don't agree. So that now the t is away. So I have minus L times c to the I minus 1, and then I get from t squared, I get a plus L times the e minus 2. Yes? That's the coefficient. Yes. Could somebody please not? Yeah, so, yeah. Is it okay? I mean, what do you get? Well, the first contribution you get is the ith coefficient here. It's just coming from the 1 here. Then the I minus 1th symmetric product will contribute from this T and this LT, yes? And then the degree of, the term of degree I minus 2 of this vector, which is the C to the I minus 2, will contribute from this T times L times T. There's nothing to it. Yeah, but then you stare at this formula and note that Ci over the Jacobian, and since I have a point, so I don't mind but the degree, yeah, this is a projective bundle with fiber. Yeah, now you tell me. It's P to the degree plus 1 minus G. Yeah, for I bigger than 2G minus 2. Yes? As we saw yesterday in Gabriel's talk. So, and we know from a long time. And then you fill this in here. Yeah, I mean, because I is bigger than 2G, we can apply this remark to all these 4 terms. And then you see you get 0.
I minus.
Right. Thanks. Yeah, and then you get this formula.
And the statement on Moduli trivial operations
Yes.
works equally well if it is étal, is trivial in the étal.
No, then it's wrong. And you can see this immediately if you just take a two-sheeted covering of your Riemann surface.
Yeah.
Then the hot structure of the covering will not be 2 times the hot structure of the base curve. Yeah, I mean the cohomology of the top is just a non-trivial Z2 module.
Yeah.
It's just not true. And this is a dangerous thing. I mean, you can, but here, you know, I mean, this vibration really comes from a vector bundle, so it is locally trivial. Okay, so that's, yeah, so I want to make one more remark here. You fit in this black box. The same argument shows you, this also implies that the class of the Picard is actually P of 1. Yeah, this you just find by noting this thing and computing the coefficient. So that's the first moduli space we calculated the motive of. I mean, of course, you knew it before, but we gave an expression in terms of just the class of the curve. And it's sort of, I mean, if you look back of what you have done, this is a bit of a funny formula because it really relates to all these other Jacobi maps which are not vibrations. Yeah? And it just puts them all together. Yeah, sort of. Okay. And maybe I should say that Kapranov does a bit more. Namely, he also proves a functional equation for the zeta function in a purely geometric way, and it just follows from shadow duality in the setup. Yeah, so it's sort of a very nice geometric way to do it. Okay. So now to moduli spaces. So this was the introduction of K0 varieties. And the only thing you have to take home is that writing such a class is just a funny way to keep track of the cohomology of the thing. Yeah, of the Euler calculus. So how do we want to apply this to moduli spaces? And this is So the aim now of this talk is now to compute the class of, so aim is to fix again my smooth projective curve and first I want to do the stack thing. So since at the beginning of this workshop there was a school on stack, so I just use it, and otherwise you have to complain. So this is the stack of vector bundles of rank n and degree d on C. And if there's time at the end, then I will also tell you how from this calculation you can deduce the same thing for the moduli space of semi-stable bundles. Yeah. This is, but so I mean, this is sort of like you know, and we saw on Tuesday, we were reminded of on Tuesday, this is sort of a bit like this Atiyah-Bott computation. Yeah, the Atiyah-Bott computation first gives a space parameterizing all vector bundles, and there they find a very nice result for the cohomology, and then they deduce the semi-stable thing by subtracting a cohomology coming from the Harder-Simon strata. So this is something we would like to do here in an algebraic way. And so this computation was first, so this is now due to, so this is all due to Behrendt and Dillon. So building on previous work of, let's put the names on it, Jochen and Letizia. So this is a much older article, and in this article they essentially do this by, they don't talk about stacks and all this, but the geometric construction is already there. And they observed how to do this in a stack theoretic context. And so first of all, we have to define what we mean by the class of a moduli space, moduli stack, in this K0 varieties. Yeah. So this is the first thing we should do. So, and there I would like to, so how to define the class of an algebraic stack. And we will not do this for all algebraic stacks, but only for some. And this was, as I said, this is all due to Behrendt and Dillon. I mean, to define this class, there are other authors which have done similar constructions independently, I think. I mean, there's an old work of Tuen, there's work of Joyce, and there's work of Ekedal, and I don't know the interdependence of these things. But the key idea you can also find back in Behrendt thesis already, so it's fair to. So what do you do? Well, you observe that, of course, so as Ignacio rightly observed, being a Zariski locally trivial fibration is quite restrictive. Yes? But there's one class of fibrations where we know that this is actually true, and this is GLN bundles. So the node GLN bundles. So GLN bundles are the same as vector bundles, so these are locally trivial. So if you have such a bundle, so if you have written your variety, let's first take a variety X, if you can write it as P times GLN, then you know that the class of P is the class of X times the class of GLN. So if we want to define classes for quotients, and stacks are just, I mean, for today, stacks are just a way to make sense of quotients when the group action is not free. You have an immediate idea, well, you have to define this class, but you know what this is and this is, so you just define it as P divided by the class of GLN. Yes? Unfortunately, GLN is not an invertible class in this ring, so we just invert it. Yeah? So enlarge. So this is a ring which has also been studied before. So pass to, so need to invert the class of GLN. And this we do in this ring. This is called the dimensional completion. So it's take this ring, and then you invert the class of the affine line. And I forgot to say this. I mean this, and then you complete. So this is called the dimensional completion. And essentially what you say is just that, well, in this ring you will have classes that look like L to the minus n times x. And you complete in the way that's saying that this will go to 0 if n goes to infinity, or rather if n, if the dimension of x minus n goes to minus infinity. Yeah, you just think of 1 over L as a class having dimension minus 1, and then you just complete with respect to this filtration that you have. Yeah?
Can you repeat that last thing?
So you first invert the class of L. So in this new ring, you will have classes that look like L to the minus n times x. And yeah, of course, and then you can just filter this ring by classes of having dimension smaller or equal some number. Yeah, smaller equal to minus n, say. And you complete with respect to this filtration. Yeah, then something funny happens. The first observation is maybe that now L minus 1 becomes invertible in this ring, because this is you tell me how to do this. So L minus 1 times 1 over 1 minus L minus 1. Yes? And this is L minus 1 times the geometric series. And this is an element in here. Yeah? So this class has become invertible, and by the very same argument you see that this class has become invertible. And of course, whenever you do such a thing to this ring, you have to check that your ring is still non-trivial to make sense of the statement. But I mean, you still have this morphism to Hodge polynomials, and there, I mean, the class of L is mapped to the polynomial u times v. Yeah, so this is non-zero, so you can localize in here. So in the second, maybe I do this here, and still have. We still have an E polynomial. And you just have to invert the class which is given by L. Yeah, so this, not that L. Okay, so yeah, now we can proceed. Now Behrendt and Dillon say so many stacks you will encounter. I mean, for example, if you look at how you describe the moduli space of vector bundles on the curve, and even if you construct the coarse moduli space, how do you do this? You take a lot of you make your degree large, take a lot of global section, and say, well, you can obtain it by a quad scheme divided out by GLN. Yeah. So many of these moduli spaces will actually look like some variety divided out by GLN. So if a stack, so for a stack is an algebraic stack, M is given by taking some variety. Yeah, so now I have to apologize. I should have avoided this, but it's sort of standard notation. So in the stack world, people often denote the quotient, the stack quotient of a variety by this type of brackets. And unfortunately, this type of brackets is also often used for the Grothendieck. And I hope that there's no confusion. I mean, I should. I can't. So this is the stack quotient. Then you just define. Yeah. So now it becomes problematic, but maybe you bear with me that this is not. I mean, this will go away in a second, so it's not. So in case there are varieties. Yeah. You just define it like this, and of course you have to check that this is well defined, but I mean, so saying that if you have two presentations like this, then they give you the same class, but this is very easy by using this statement that GLN bundles are locally trivial. Yeah? So it's well defined because GLN bundles are locally trivial. So also, so the same applies, same gives definitions for M, which you can write as a union of xi. Yes, you can just stratify it like this. And there's a general result that any stack such that the algebraic stack of finite type such that the automorphism groups of stabilizers are, the automorphism groups of points are affine can be written in this form. We will not use this because we will only use GLN vector bundles on curves, and there the Quadstein construction gives us such a decomposition. Yeah. Yeah. Okay, so now the 20 minutes left, that's good. So e.g. 1 and d is of this form. And so the aim is, the question is, so what is okay. And there's a very nice argument of Bifekion and Letizia, which gives this class. And they, namely, what do? They say, well, we just try the same approach that we did for PIC. For PIC, we just said that, well, we compute the class of the Picard by saying, well, it's just the class of a symmetric product divided by the class of the projective line, projective space. Yeah. So this gave us the PIC, and we will try to find an exactly analogous vibration for this space. And it's funny that this is possible, I think. I mean, this is, in some sense, this is the nicest computation of the cohomology of the moduli space of vector bundles that I know of, in the sense that it's, yes. Because in some sense it's the very most naive approach that you could try. It's sort of amazing that it works. So what do you do? So yes. So we look at some diagrams. So what would be Ban and D? So we try to look at something which is like the symmetric product for the curve. So what was the symmetric product? This was, we endow our vector, our line bundle with a global section. So let's just pick n global sections. So what do? And we look at the following space. Yes. Oh, sorry, I think I have to put it more in the middle. So above this space, I have a universal vector bundle, which I call E universal, and I will just write it as hom of E universal to some fixed vector bundle, and I don't choose sections, but I choose the dual of it. So fix the divisor. So I hope this is an intuitive notation of this. So this is just the space which parameterizes a vector bundle E together with a homomorphism from E, so together with a phi from E to tensor n. Yeah? So that's just hom. And, well, if the degree is large enough, then this will just be a vector bundle over this thing. Yes? So inside here, And now I have to make sense of what means degree large enough. So inside this, I have to look at the following space. And I will be a bit vague about the exact parameters because they don't really matter. I mean, of course, you have to do the computation once what the exact parameters are. So this is the subspace. So this has a large open substack, which just consists of vector bundles, such that the instability of the vector bundle is not too big. Yeah. So that the degree is this means just that the slope of the maximal destabilizing bundle is bounded by h. Yeah, such that the degree of instability of E is less or equal to h. Yeah, so this. Yeah, does this make sense? Okay, so if I fix first h and then do my divisor large enough, then I will know that by Riemann-Roch there's no x1 term here for this thing. So I know that this will be a vector bundle. So let me call this Hom A universal less or equal to h. And this is yeah, maybe I will continue this diagram to the left in a second. But I will wanted to start doing a computation. So if I want to compute this class 1 and D, then first of all, this will be the class of Ban and D less or equal to h, plus the class of the complement. Yeah, but the complement will have high codimension. I mean, arbitrarily high codimension if I choose h large enough. So this is some rest. This is something of dimension less or equal to, say, minus n of h. Yeah? Does this make sense? So if I make h large enough, then the codimension of the complement will get arbitrarily small. So this space will become of arbitrarily small dimension. Yeah? So as long as I pass to the limit in the end, I can forget about this term. Yeah? I mean, I only want to compute this class in this dimensional completion, so up to any order. Okay. So over this thing.
What's the reason why the dimension becomes more and more negative?
Yeah, you just mean.
I mean, intuitively, it's clear that as h becomes bigger, you are capturing more and more pieces of Ban. But
yes, you just mean you compute. I mean, you know what the Hadamard strata are. And you compute what their codimension is. This is just given by, I mean, this is this normal bundle computation. This is just something which is described by some x1s of line bundles, and you just compute this dimension by Riemann-Roch, and you find, well, the codimension gets large and arbitrarily large. Yeah. So since this is a smooth space, and you have a subvariety of high codimension, its own dimension will be smooth. Alternatively, you could just compute the dimension of all the Hadamard strata, and this will get small. I mean, maybe. Is it okay? I mean, maybe I give an example. Yeah. Yeah. Okay. Okay. Yes. No, I have 10 minutes, so I don't get it. I mean, if you go in rank 2. Then very unstable bundles are extensions of a bundle of large degree by a bundle of very small degree. By Riemann-Roch there are no extensions, but there are lots of homomorphisms from the lower to the upper. So this space will be, the stack will be 2 copies of pig divided by the automorphism group, which is a large affine group. So this will go to. Okay, now we do the same thing here. So now here we can go to the top because this is a vector bundle. Of rank, yes, I can compute it. You can as well. So it's n times n d minus d plus n square 1 minus g, if I'm not mistaken. Yeah, something like this. Yes, it's just Riemann-Roch formula. So this is the same as this Hom in hom e less or equal to h divided by L to the, it's a vector bundle, so it's L to the n times, oh, it's videotaped. I shouldn't dare writing down this wrong formula. Okay, so please correct it if it's wrong. So. Plus, yeah, but plus this rest term, plus dimension we don't care about. Yeah, now I claim that I can play the same trick upstairs with a slightly weaker bounce, but I don't care. Now yes. Okay, now, so why is this class easier to compute? Well, let me go back. This class would be easier to compute. So, why am I more happy upstairs? Because inside of this homomorphisms, I have the injective homomorphisms. Yeah. So I have an injective homomorphism from an arbitrary vector bundle into a fixed vector bundle. Yeah? But this is just the space of modifications of this one fixed vector bundle of some given length. Yeah? So this is just a quad scheme. Yeah? This is the space of modifications. So this is the same thing as the space parametrizing surjections onto tau, where T is the torsion sheaf of length. Yeah, well, the difference of the degree. So this is n times d minus d. Yeah? And I would like to call this is the modifications of length nd minus d of the fixed bundle O minus d. Yeah? So this is a moduli space that we understand well. Yeah? Yeah? So I mean, if the difference of the degrees would just be 1, then this would be just describing one point in the curve plus a one-dimensional vector space in the fiber above it. Yeah, so it would just be the curve times p to the n minus 1. Okay, so now let me continue this computation. So I claim that again here we have high codimension, and I claim that again for a large degree here we have high codimension of the complement. Yes? So I claim this is equal to hom. Yeah, first we go to the universal. L to the same degree. So let us call this number. No, I just plus terms of dimension less or equal to minus n of h. And I claim that, well, you can also compute what the non-injective homomorphisms are. Yeah? They have to factor through a subbundle of smaller rank, and you just estimate this and find again that for d large, the codimension of the complement will go to infinity. Yeah, this is a computation you just have to do, but it's not difficult. And I claim that this is hom injective. So this is an easy exercise. nothing. Plus dimension small h over tau. And of course this number n of h, I mean, will be computed at the very end. It depends on h and on d. Really.
I don't understand the logic of the previous equality. So what is the difference between this term and this? I mean,
So again, this is an open sub-thing of this. And again, I claim that the complement, I mean, the complement is something like not really a vector bundle, it's a vector bundle over this complement, which we already know has small dimension. So this complement here actually turns out to have small dimension again. Yes? Yeah? And so then I can go here, and again I have to check what is the codimension of the complement. And again I can compute this. I will not do it on the board, but you can do it. I mean, yes, you can do it over coffee or ask me again. So, but now this is, so the only thing we need to compute, so this is essentially this modifications of length ND minus D of this one fixed bundle. Divided to L to the something plus small terms. So the only thing that you have to compute is this place. And I just give you the answer. And then you tell me how much you want to know about it. And it's sort of funny that let's say some length L of O doesn't even matter what bundle you put here. But let's take this. And then I tell you what this is. So I told you that if this length would be 1, then this would be the formula, yes? So if L would be 1, then to give a modification of length 1 of this vector bundle would just be I give you a point in the curve and a one-dimensional subspace of the fiber of this vector bundle. So I will get this class. Now I do this L times, and I don't care about the order. And this is of course cheating very much, because I could choose L times the same point, and then I have lots of different types of modifications. But for the class in the Gruppendegree, it turns out that this doesn't matter. Yeah, I think this is it's very funny that in none of these articles this formula is actually written down, because they only care about terms up to degree something, and they sort of don't give this formula, but this is actually what you find. Yeah. I mean, this is a very funny formula in the sense that the space of modifications, you know that it is smooth. Yes? Such a symmetric product is never smooth, because it's a symmetric product of a variety of dimension larger than 1. I mean, this equality just says that there's a cut and paste procedure to cut this into pieces and to glue them back together again to some smooth thing. Yeah, so it's sort of funny. And the proof is actually not so difficult. Maybe I just sketch it. So the idea is the following. Is following. As I said, the vector bundle really doesn't matter at all which vector bundle of modifications you put. It's the following that you consider. I mean, you have the space of all modifications of your bundle. So what you can stratify it into saying, well, you just take the inclusion of the first one, of the first summand. Yeah, this will map onto some subsheaf here. Yeah, so this will map onto some quotient of this bundle, but this is just the divisor, so this is just O of the divisor divided by some other divisor, they call it D prime times the same bundle. Say O of D minus D prime. And some quotient minus I'm writing too small. And this will be a quotient of dimension 1 less. And so if you fix so the space of modifications of length L, let me drop the bundle. This is the disjoint union of the modifications of these extensions where the subbundle maps to something of length, say I. Yeah? So it's the disjoint union of I equals 0 to L of, well, you have a modification here and a modification there. So it's modifications, I have to put the O to the N here, of O to the N minus 1 D times, let's put the class, I'm sorry, times, well, the modifications here, this is just of dimension L minus E times the symmetric product times, and then you have to count how many extensions there are, and they turn out to be L to the dimension of home from here to there. So this is N minus 1 times I. Yeah. And note that if you take C times Pn minus 1 to the L, you just find the same recursion formula. This is the class of C times Pn minus 2. So this has a to the L minus I times C times and so this is the proof. Yes. Just find the same recursion. So these extensions just are a vector bundle over this product, and so you find this formula. Okay, so my time is up. I'm sorry. So I just want to give you the formula now. Now we have computed this, and we have to go take this limit to infinity, and if you do it correctly, then you find the following formula. This is L to the dimension of the bundle space. And this is actually this exponent is actually this times, and you find P of 1 divided by times the product from I equals 2 to n P of L to the I minus, it's just the zeta function of the curve. So let's say zeta function L to the minus I plus 1. So you can write this in a bit of cleaner way. So this turns out to be equal to the product I equals 0 to n minus 1 pi L to the I. So here I use the functional equation for the zeta function, but just to give you the formula once. just to give you this formula once, because here you see the Atiyah-Bott result back. I mean, this quotient, if you look at this, so the numerator, if you expand it in a geometric series, this just looks like a polynomial algebra in n plus n minus 1 generators. And the denominator, remind you that the P was the cohomology of the P car. So will give you an exterior algebra here, and you see the Atiyah-Bott result. So this gives Atiyah-Bott result. Okay, sorry, I'm over time then. Thank you.
Questions, comments, remarks?
Have people done similar computations for moduli spaces or stacks of vector bundles on projective plane, K3 surfaces, whatever?
No, I don't think so. I don't think so. I mean, so what we have done is, and what we'll talk about next week maybe is for Higgs bundles on curves. You can you can use this similar technique. I mean, the problem is that the fact that you have such an easy presentation, yeah, so this nice to have this nice vibration. This is a very exceptional thing, and I don't know whether similar things exist for higher dimensional varieties. I mean, it's not completely unlikely, but I mean to do all these dimension estimates, you use the Riemann-Roch a lot, and so yeah. I don't know whether the H2 kills you or not. I mean,
And what about replacing GLN by another?
yeah, that's a good question. This is actually in this article of Behrendt and Dillon. They put down a conjecture, and they put down a conjecture that the same formula should be true for G bundles, but not in this Grothendieck ring, but in the Grothendieck ring where you import furthermore the relation that for G bundles you get multiplicativity. And I think that, so I talked to Dylan about this. Yeah, I think that actually a result of Totaro tells you that in this Grothendieck ring, this conjecture would not be true. Yes, I mean this.
In this Grothendieck ring.
In this Grothendieck ring, the analog for G bundle would not be true, and this is some you could see some torsion phenomena in BGs, which, yeah, it's hard to believe that you can see any torsion in this Grothendieck ring because it's an Euler characteristic, but still you can, and so it would not be true in there. But if you do this G bundle inverting, maybe it is. But the main obstruction to proving this is to find such a nice presentation. And this is not clear to me. I mean, this is a, yes. I mean, this is a very funny result because it tells you that if you fix one vector bundle and modify it to some large length, then you will get all vector bundles with the same number of times. Yeah, if you do this is a stabilization thing. And for G bundles, this is not, I mean, this is a similar thing seems to hold, but the stabilization is much more complicated and I don't see it in a geometric way at all. And this is, I mean, in number theory, there's sort of equidistribution results give you sort of similar thing, but it's not clear for G. Okay, so the answer is there's a conjecture for G bundles, but it's only a conjecture right now.
Our next talk is at 3:30 with Tony Mantif. We'll go and it's like Jochen to this nice master class.